The building being analyzed is the Jack Copeland Blood Transfusion Center, operated by National Services Scotland, which is located on the Heriot Watt Research Park. The building has been active since 2017 and is one of the most advanced blood centers in all of Europe. The floor plan of the building is 11,500 square meters. The building has been constructed for natural flow and does not have columns obstructing views. Instead, a mixture of glass and glazing has been used throughout the building. The glass allows area to be kept separate, but still allows people in the building to see each other, and this helps with a sense of connection. High-spec glass has been used in the labs to help maintain air tightness. The arcade helps to form the main part of the center. It removes barriers and allows daylight and fresh air into the building. The building also maximizes the most amount of sunlight possible, with labs receiving indirect sunlight to keep them at optimal conditions. The most used material within the building is glass and glazing. The site has good potential to utilize and incorporate more sustainable technologies, which could increase the efficiency of the building as a whole. The current building uses a gas-powered combined heat and power system. It is quite efficient, but gas is not a sustainable source of energy. The building could reduce its carbon emissions by using on-site supply solutions. Wind power could be utilized through either roof-mounted or pole-mounted turbines. There are large plots of land surrounding the blood transfusion center which would be suitable to install a number of small-scale wind turbines. The site has the advantage of being outside of the city, reducing the likelihood of disturbance or interference through other structures. Micro-hydro technology has limited potential to generate energy for the center. The center is located near a small section of water, which may be possible to utilize in order to create a small form of micro-hydro energy. The site has large potential for the use of systems such as ground source heat pumps. The land surrounding the center provides a suitable place for digging and installing a heat pump to extract heat from the ground. There's plenty of clear space and would keep the site with a natural and untainted look. Data from the table suggests that from late spring to early autumn, the center experiences less rain and increased sunlight, making those times of the year optimal for solar energy generation, while the months closer to winter will be less effective for solar generation. A major aspect of the building is its laboratories, used for the processing and testing of donated blood and tissue samples. Laboratory environments consume large amounts of energy as they require constant mechanical ventilation. Laboratories also have extensive scientific equipment and appliances running simultaneously, some 24/7. Plasma from blood must be stored in freezers and platelets must be kept at room temperature. To maintain the requirements, multiple large fridges and freezers must be running continuously. Heating, ventilation, and air conditioning is needed in the labs year-round. In winter, heating will be required throughout the building as the outdoor temperatures in Edinburgh drop, and adversely, air conditioning in the summer to maintain a safe working environment. Electric lighting will be needed throughout, as Edinburgh usually has overcast skies. Summer sunlight may reduce some, but not all, need for electrical lighting. Electrical consumption during the year stays about the same. There's a slight increase between June and September as the air conditioning systems may be turned on to maintain a comfortable room temperature. Natural gas use increases dramatically in the winter as it is required for heating. Offices see a surge in energy demand during the working day when people occupy the space. There is a surge in natural gas usage in the morning as heating is turned on. During summer, the natural gas consumption falls during the day, at lunchtime, and mid-afternoon. This may be due to people leaving the building during their lunch breaks and heating being turned off at the hottest part of the day. There's also a baseline heating load at night, as some of the 24/7 areas, such as the security office and reception, may be needed to be heated at night. There's a small, steady usage of electricity during the night, and the electricity demand increases significantly around 5 a.m. when the systems are turned on for the people to start working. The electricity consumption peaks at midday when the building is at its busiest. The demand drops slightly at 5 p.m. when workers leave and drops significantly down to its baseline load around 11 p.m. This table provides a more in-depth breakdown of electricity use by the center. Currently, natural gas is used to heat the building via a gas central heating system. Natural gas is a combustion of gases which are high in hydrocarbons. It is not a renewable resource of energy. Natural gas is retrieved from gas reserves that are deep down in the Earth's rock. The building receives its electricity directly from the national grid. As of 2015, 42% of Scotland's electricity comes from renewable sources, 35% from nuclear power plants, and 22% from fossil fuel combustion. The future energy demand profile of the Blood Transfusion Center is expected to stay the same due to the nature of the building, as laboratory use demands high energy. A large amount of energy use in buildings is related to internal heat gain. Reducing this will lower electricity use and cooling load. Using LED bulbs could help achieve this, as they use up to 75% less energy than incandescent and come in a variety of shapes and light levels. Other techniques may include spacing equipment runtime to be even throughout the day and varying office and lab operating times, leveling energy demand. Solar photovoltaic, or PV panels, convert solar radiation into electricity, helping to reduce the building's total energy consumption and annual running costs. For the Blood Transfusion Center, monocrystalline panels were selected as the most energy-saving option, with a typical efficiency of 15% and a peak power of 1 kilowatt peak, ideal for the Scottish climate. In addition, these cells have to be installed on the 2,500 square meter roof and directed southward under an angle of 30 to 40 due to the northern hemisphere. The system does not require ventilation due to the cold climate conditions and a modest overshadowing factor of 0.8. Advantages of monocrystalline photovoltaics include low maintenance costs and high heat tolerances, reasonably long lifetimes and durability of over 25 years, better performances than other styles of PV material for low light conditions, and producing own power protects against rising energy prices. It was calculated that the total photovoltaic output of the following system would be 270 megawatt hours per year. They would reduce the Blood Transfusion Center electrical demand by 13%. The proposed photovoltaic system could recoup installation costs in 11 years' time. Solar thermal panels are devices mounted onto a roof that absorb the sun's radiation and use it to heat water stored in cylinders. They are the most efficient way to reduce natural gas consumption. Solar thermal panels can provide 50 to 60% of domestic hot water needs. They work in cold climates, overcast weather, and strong winds. The total solar thermal panel output of the following system would be 98 megawatt hours, reducing the JCC blood transfusion natural gas usage for hot water by nearly 5%. It was calculated that a vertical ground source heat pump single U-tube system would produce 427 megawatt hours a year, thus reducing the Blood Transfusion Center's total natural gas consumption by 20%. However, installation of ground source heat pumps can range from 12 to 30,000 pounds. A fuel cell is a device that generates electricity through a chemical reaction. Every fuel cell has two electrodes, called an anode and a cathode. The reaction that produces electricity takes place at the electrodes, run by hydrogen. Fuel cells convert chemical energy directly into electricity without a combustion process, making them highly efficient. High power density allows fuel cells to produce large amounts of energy in a small space. Fuel cells are extremely quiet in operation, and this allows fuel cells to be used where noise pollution is undesirable. Fuel cells also have no moving parts, making them easy to maintain and less likely to break. It was calculated that the proposed fuel cells would generate roughly 473 megawatt hours. The total energy demand of the JCC Blood Transfusion Center would be reduced by 15%. However, by producing two types of energy, 60% electrical and 30% thermal, energy savings could total up to 40,000 pounds per year. Reaction turbines are highly efficient and depend on the pressure produced rather than the velocity of the produced energy. They are often in large-scale power sites. Impulse turbines are commonly used for high-head microhydro systems. They rely on the velocity of water to move the turbine's wheel. Other microhydro systems include monofloat and free stream systems. Monofloat can be anchored to the bottom of a river and completely submerged, and they provide three-phase AC power from the magnet generator. Free stream turbines is installed on the bed of a river and also produce three-phase AC power from the magnet generator. Free stream systems can produce slightly more power than monofloat systems under the same water velocity. Wind is a form of solar energy caused by a combination of three concurrent events. the sun unevenly heating the atmosphere, irregularities of the Earth's surface, and the rotation of the Earth. A wind turbine turns energy in the wind into electricity. The stronger the wind, the more electricity is generated. How consistently the wind blows also affects the power produced. Wind turbines can either be connected to the national grid or stand alone, storing the wind energy they produce in a battery. There are two types of small-scale wind turbines. Rooftop models, which generate from 1/2 kilowatts to 2.5 kilowatts, and pole-mounted domestic turbines, which generate 5 to 6 kilowatts. Cost of small-scale wind turbines can reach up to £3,000 for a roof-mounted microturbine, and up to £30,000 for a 6-kilowatt pole-mounted wind turbine. Although small roof-mounted wind turbines are cheaper, they generate much less electricity and in this case would be ineffective. This table shows an average output of a pole-mounted turbine with a wind speed of 5.6 meters per second. The graph shows the average wind speed per second and the compass shows the direction of wind from the NOABL station near the Blood Center from 2000 to 2010. The Energy Saving Trust does not recommend installing a domestic small-scale wind turbine in areas with wind speed of less than 5 meters per second. Considering this information, the most cost-effective option to use on site would be a pole-mounted turbine. For it to work effectively, there should be no obstructions with the turbine, with the building being a minimum of 150 meters away and the turbine being mounted at a height of a minimum of 9 meters. Given the space of the site, it can benefit from installing multiple pole-mounted turbines and by positioning them as high as possible, maximizing the energy produced. In closing, our group would recommend using the ground source heat pumps, photovoltaic panels, solar thermal panels, and fuel cells. The GSHP would bring a 10% gas reduction in heating. Photovoltaic panels would reduce electrical consumption by 12%. Solar thermal panels would reduce gas for hot water heating by 5%, and fuel cells reducing electrical consumption by 12%.